So, Brittany, I did record last class.
Okay.
That's the one you missed, right? Mm-hmm. And so I'll try to make that available.
I was going to ask you if you're going to post the slides, too.
Oh, I think I did, actually, last night or something.
Okay. I would
Yeah.
check, yeah.
The answer is no. Okay.
No.
Okay. Something went wrong with that then. I will fix that too. Okay, so last time we were playing with quack, right? And I found the level of the room. We're going to continue doing QAP stuff, and basically what QAP is of course a technique for testing hypotheses. And there are, I should tell you, multiple statistical methods out there. There's actually kind of three kinds of statistical methods in networks. You may think of it as all statistical, but only in the sense that there are measures. But in terms of inferential testing hypotheses, there are just really three families. One is QAP, which we've covered. The other is ERGM, which is exponential random graph models, and the other is UCINET, which is basically ERGM for longitudinal data. And let's just talk a little bit about this. We'll summarize what we did last time. What we'd like to be able to do is be able to determine whether one tie entails another. Like, we want to know whether marriage ties between Florentine families in the Renaissance predict business ties among those families lagged, a year or something. So we want to be able to see whether one kind of tie entails another. We want to regress one kind of tie on the other. So we might believe, for example, that physical proximity leads to friendship. So we would make proximity the x variable and friendship the dependent variable. And maybe we also have some other kinds of controls and things. And we could regress that there's no real problem with doing that. It might be, just to not offend sensibilities, we could go the other way around. Let's predict that people who are friends tend to move closer to each other, so that the dependent variable is not 1, 0, and so we don't have that question about should we do logistic or something else. If we wanted to run that regression, we could just string this matrix out into a big long column that's 12 long. Well, actually, since it's symmetric, it's just got 6 actual values, right? It's got Jim to Jill, Jim to Jen, Jim to Joe, Jill to Jen, Jill to Joe, Jen to Joe. So there's 6 cases. And then there's 6 cases over here, and we could do that correlation in SPSS. And the parameter estimates would be exact. The only problem is that the significance would be wrong. And that's because SPSS assumes that the observations are independent of each other, and they're not. So we have this autocorrelation problem. And they're not for all kinds of reasons, right? Like, one of them has to do with row effects. Like, Jim here is just a very sort of extroverted, just has a lot of ties. So there's ones all the way across. So the fact that the Jim to Jill tie exists is actually kind of dependent on the Jim to Jen and the Jim to Joe, because they all are part of the Jim factor, and they're not independent. And the same with the columns, because again, there's the Jim factor in the columns, and there's also, like, the Jill factor. Nobody really seems to like Jill, and Jill doesn't really seem to like other people. So there's the row and column effects. But if it were just row and column effects, we could actually control for those. But the thing is that there's all kinds of dependencies in these networks, like the one that I pointed out before about proximity, where if the distance from A to B is 5 and from B to C is 5, then the distance from A to C can't be 15. It's got to be less than 10. It's got to be 10 or less. So there are all kinds of complex interdependencies here. What QAP lets you do is to do that correlation and control for the dependencies. And the really cool thing is you don't have to know what the dependencies are. You don't have to be able to write them down. It just controls for all possible dependencies simply because of this permutation method that it does. Now, it doesn't tell you what the dependencies are, and occasionally you might want to know what kinds of autocorrelations are going on in your data. So, for example, some things that people notice and care about is reciprocity. Often, a tie from I to J increases the probability of a similar tie from J to I, because there's a norm of reciprocity. I give you something, there's a strong tendency that you'll give me something back. This is the common node interdependency here, where the IK relation involves I, and the IJ relationship involves I, and if I is very valuable, then it increases the chances of both. If I is very introverted, then maybe the probability of both are lower, but they're related. Another one that we notice a lot is triangles. There's a strong tendency for people to be friends with their friends' friends. Friends with their friends' friends, yes. So you have a person A here who is a friend B, and B has a friend C, and eventually A and C meet because B here introduces them or whatever. But there's just a strong tendency to create these little sort of closed triangles. One of the main processes by which we meet people is through the people that we already know. So that's a kind of dependency, right? It means that if this tie exists and this tie exists, the probability of the third leg appearing is much higher than by chance alone. And then there's these kinds of things. These are kind of poorly diagrammed, but what it means is that there are some people that just have a tendency to attract ties, and those that already have a lot of ties are the ones that new people coming in the system gravitate towards. It's like you enter the system, you realize that one person is like really central, and you tend to also develop a tie with that person. It's known as preferential attachment. So, given that we can give names to all these different things, and they're sort of social mechanisms, we might want to actually find out if they're going on in our data. That's where ERGM comes in. Now, ERGM is an exceedingly complex model. It stands for exponential random graph. The M is for model. And it's basically a kind of logistic regression, but it is ridiculously hard to understand. I cannot stand them personally. I find the parameters really hard to interpret. But they have certain benefits, and one of them is that they can tell you whether your network has a greater tendency towards reciprocity than you would expect by chance, a greater tendency towards transitivity, etc. All these different things, and there's like dozens of these different kinds of micro-level configurations that your network might tend towards or tend away from. Right, so it's like an advice network has a strong tendency to be non-reciprocal. If I give you advice, typically you don't give me advice. So it has this really cool advantage, and all of these tendencies are assessed while controlling for the other one. And that's really helpful too, because some of them are really similar. So for example, suppose your network shows a lot of transitivity. It could be because of that process whereby your friend introduces you to his friend, or it could be an artifact of homophily. Homophily is like where you have a tendency to have ties with people who are like yourself. So let's say there's gender homophily. I'm male, I tend to orient towards other males, and that means that there's going to be transitivity, because if you and I are male, and you and somebody else are male, then that means that person and me are male, and so we all have a higher probability of making a tie, and it looks as if it's transitive, but in fact it's just the fact that it's homophily that's going on. We're all the same characteristic. Hopefully that makes sense. So, The actual model for an ERGM is a nasty thing. I stole this slide from an ERGM guy. I love the way it's the simplest model. And the way it's phrased is that the probability of your network, and I'm talking the entire network, the probability of getting exactly your network, where Fred is connected to Jane, but Jane doesn't like Bill, and so on, every single tie there. The probability of that network is a function of all of these coefficients where, well, the coefficients are the thetas here. The G's are graph statistics. They're counts of things. They're counts of things like the number of transitive triples, the number of reciprocated dyads, the number of, I don't know what's, paths of length 3.
So in a non-directed model, for example, that reciprocated dyad would always be full, and so the covariant, basically the coefficient of the covariant on that would be 100%.
Yeah, it actually sort of screws up the model, so you have to just tell it that,
Right.
by the way, they're all connected. But yeah, you're right. It would be like as big. It would be huge. And they're not. And the 0 means that microconfiguration is occurring at chance levels, but there's no maximum level. So it could be 2 or it could be 75 or whatever.
Right, but if every possible observable combination occurs, then it assumes 100% probability.
So yeah, it would predict 100% probability, right? Yeah, the parameter itself would not be 100; it would be some number.
Right.
Yeah, exactly. And of course, each of these parameters have a standard error. So the way you would tell whether it's significant is just by dividing it by its standard error and hoping that it's more than 2.
Will it error out at that level as it approaches perfect correlation?
It would actually give you a warning, and because it screws up the estimation of the other parameters, and so it would just say, you would turn on a switch that would say, don't even try to estimate this one, fix this one at its maximum level. This model can actually be translated algebraically into a tie-level model. Let's see. Well, we'll get to that. Well, here's a restatement of the model that we saw a moment ago. It's stated a little bit better. The probability that the network Y is the exact network that you happen to see, the little y, is this function that's sort of like at a log level, it's a linear function of these parameters times these network statistics, which are all counts of these microconfigurations. We can convert this into a kind of logit here, where so it's linear in the logit, and the thetas are the parameters that we're estimating. The deltas are the change in the count of the microconfigurations due to adding a particular tie to the network. So if you added a tie from I to j, so it went from a 0 to a 1, how much change would that be in the number of transitive triples? How much change would that be in the number of reciprocated dyads? How much change would that be in the number of what are called K stars and all these other little microconfigurations that you can choose from? So it's a change model. Now, so what is it good for? Well, it's really good for measuring or assessing the extent to which your network has tendencies to form certain kinds of microconfigurations, and including things like is there a tendency for people of the same gender to be connected to each other? Is there a tendency for nodes of high degree to attract ties with other nodes of high degree? So anything that you can frame, that you can write down as a micro configuration right around a node, we could count up as a statistic, and then we could figure out the contribution that each tie in the network makes to that count. Now, estimating these things is an absolute bear. You can only do them with small networks. They take forever. You have to do them with Markov chain Monte Carlo, the MCMC models, and it's and then interpreting the coefficients is an absolute art, and they vary widely by taking one parameter out, and then suddenly everything changes. So it's a technique that's in development right now. There are absolute zealots, though, and there are people who say, if you send in a paper that has a significance test in it and it's networks, there are people who will say, oh, you have to use ERGM. That's the thing, yeah.
When you say smaller network sets, how small do you mean?
Like 50 nodes. Officially, the software says something like 1,000 nodes, but the only way to do that is to use it on parallel R on a supercomputer. So in practice, you're stuck around 100 nodes or something.
We do have a super.
Do we?
Yeah. One teraflop.
Who's we? Like a consortium?
University of Kentucky.
Just by ourselves?
Yeah. It's over there in the building on Rose Street, just north of the campus.
I didn't know that.
Visualization center.
Oh, the Marquee.
Marquee,
Yeah.
The Davis Marquee.
Marksbury.
Parksbury.
Yeah.
That's the one.
All right.
It's in there.
God, I've been in that building. I didn't feel a presence. But,
You can do it. You can do 1,000 nodes.
all right. Well, if you want to learn ERGM, you need to learn from somebody that knows what they're talking about. I'm not even going to try. But I can tell you sort of the advantages and disadvantages. So, what can you do with ERGM compared to QAP? Well, one thing you can do is you can put in a dyadic covariate. So you could see if marriage ties tend to be associated with business ties. It basically counts up the number of times that there's both a marriage tie and a business tie, sums it up. And but what you can't do is build a linear model like we're used to doing in normal journals, right? Where we say, well, we think that the probability of business tie is a function of there being marriage ties, physical proximity, they have to be compatible company or organizations, there have to be political ties, there has to be something else, all these kind of control variables and things like that. You can't do a model like that, but you can do a bivariate model. So at that level, QAP and ERGM are comparable. And the advantage of the ERGM in that case is that it also gives you, and by the way, I'm controlling for the number of transitive triples or reciprocity, and I can tell you the extent to which those are happening in your network. The QAP is controlling for those things too, but it doesn't tell you how much they're present. It doesn't even know they're present. So QAP is really not well suited to testing overall tendencies of the network towards certain motifs, as the physicists borrow this stuff, and they call them network motifs, just little micro configurations. With ERGM, model specification is really critical, and if you discover that there is some new dependency in your data, you just know it because you know how the data were constructed. You can't just run ERGM and do it because somebody has to program that specific dependency into the program, and it takes a mathematical statistician to do it. So whereas with QAP, that just doesn't come up. You could just run it. And then there's the computational aspects of it. If you look at the listservs for ERGM and the related model Siena, it's full of users saying, I can't get my model to converge. This is the model that is theoretically the one that I want to test, but it will not converge. And It's just really problematic. Any questions about this highly detailed description? Okay, well, I want you to be aware of ERGM because I think in 10 years, ERGM will be a powerful technique that can be used for a lot of different things. And it may be a better way, like UCINET has a number of things. So I'm just going to start up UCINET for a second here, which you needn't do. But if we would go to network cohesion, we could measure things like transitivity. So that assesses the overall level of transitivity in the network. Let me just pick a network to try this on. I'm going to do Paget data. And it tells me that in the marriage ties, transitivity is pretty low, but in the business ties, it's quite high. But notice there's no significance test here, and it's being measured in isolation. It's not controlling for the fact that there's also a certain level of reciprocity, there's also a certain density of the networks, and I happen to know that the business network is a little bit more dense, which would tend to create transitivity. In fact, if you've got a network that is 100% dense, everybody is connected to everybody, there's 100% transitivity. So ERGM is good for that kind of stuff. I feel like there should be a question here. Okay.
If I wanted to model the likelihood of reciprocity using cloud.
Reciprocity we could do. So suppose we have CampNet. That's one of the few that we could do with QAP. CampNet is clearly not symmetric, right? Holly's got a tie to the fourth person here, but the fourth person does not have a tie to Holly. But there might be a tendency in here to be reciprocal that we just can't see. Suppose we predict CampNet by its transpose. So I'm going to create a new data set. I'm going to do it in the CLI. I'm going to say tCampNet equals transpose of CampNet. So it says create a new data set called tCampNet and make that the transpose of CampNet. And I could then display CampNet, and I think there's a way, here's what I could do. Display join calls CampNet tCampNet. So CampNet is the first bit here, and then here's tCampNet over here. I just wanted to put them so that I could see them side by side. So you see Holly to Pam is a 1, but Pam to Holly is not a 1. If we look over Holly to Pam over here, it's not 1, but Pam to Holly is a 1. So this is the transposed version, right? So if I predict CampNet from its transposed version, I would be saying that whenever a person sends a tie, we're expecting that there should also be a reply tie. So I could just quap those two together. I'm going to do a control Q and CampNet tCampNet and run those. And it is highly correlated and significant, which means that there is a marked tendency in this network for people to reciprocate ties. So that one we can handle in QAP. Transitivity is a little more difficult, although I'll show you some stuff. I'm just going to run transitivity on CampNet. Yeah, it's just from rule of thumb wise. That's transitivity. I don't want transitivity. I want reciprocity. Boy, that's trouble. There's nothing complicated about doing reciprocity. I hate to do this, it's my program, but I'm going to kill it. It's still screwed up. Yeah, go ahead.
So this is a reciprocity on ties.
Yeah.
How would one test a hypothesis on maybe the strength of the relationship or some form of information or benefit that goes between the ties?
Tell me more.
So let's say that I provide you with a resource and then you provide me with a different resource. When
Yeah.
you cross a network of ties, those levels change.
Yes. So we would have two separate matrices,
Yes.
and we would just correlate one with the other. So I expect that if I give you advice, that then you give me money.
So you'd have just what, a money transfer matrix and advice matrix, and you would just correlate those.
Yeah, but I would do the reciprocal of one, the transpose of one of them, because otherwise it would mean that I give you advice and I give you money.
I like
It seems wrong. You accounting people. There is something funny going on here. It's just really like flashing at us.
So ERGM is just kind of like telling you, I guess, like what relationships are in there, whereas QAP just tells you that there are relationships that are like happening.
Yes. Although I don't like the word relationships because that sounds like ties, but it's like certain tendencies to form little micro patterns, like to form a closed triad. And it will tell you, ERGM will tell you that this network, much more than than a simple by chance alone, is just a lot more clumpy than you'd expect.
So ERGM is like the probability of certain
Yes.
network formations happening.
Yes, 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 it is. Whereas QAP is really very much in the linear model. It's just predicting one tie from a set of other kinds of ties. My computer is really screwing up. Let me just try this.
Have you caught the Stuxnet?
Have I what?
Caught the Stuxnet? It's the virus.
Oh, Stuxnet. Oh. Is that the one that's for machines, isn't it? For like industrial machines? Like
For whatever.
centrifuges and stuff?
Well, I saw on your task manager you had your Bluetooth on. It can be
Oh. Good to know. Okay.
showing my weird predictions today.
Yes, you made sequel jokes and all kinds of stuff.
would you test within your network how much information from one person is getting passed on to another from, I guess, central to outer, from outer to inner? Like, is there a
Yeah. Well, let me take the simple approach. You'd have to have, first of all, an actual measure. I mean, you'd have to collect data on information passing between people, right? Now, you could classify the people by whether or not they're inner versus outer. Say we run a core periphery model, and that it just tells you this is the core and this is the periphery. And then you could see whether that predicts the pattern of information transfer. And if it didn't, it would mean that information transfer is happening between pairs of people kind of irrespective of who's out and who's in. But if it did predict, it would be, no, that variable is actually patterning which direction things are going. Yeah. And we could also do this a continuous level thing. So we could have a measure of the degree to which somebody is in or out, and then expect that more, that's sort of correlated with, it goes along with more information going in, the more that person is in.
I wasn't sure if there was like, I guess, like a percentage link to each tie, so that, like, let's say Bob's in the middle and Margaret's right outside, and then Margaret's attached to Jan. Like, if it was just like, let's say 50% of the information that Bob, who's in the center, gets passes on to Margaret, and then from Margaret to Jan, 50% of that information. So it would just be like 0.5 times 0.5, and you get like Margaret at the outside gets 0.25% of that information.
That exact model exists, yeah. And we get to it. It's There's a measure called beta centrality that does exactly that. And you as the user have to set that parameter of, like, is it 0.5 or is it 0.8? And if you set it very large, it means that long paths still count, right? Because you'd have like 0.9 times 0.9 is still 0.81, and still high. But if it's low, 0.5 times 0.5 is just going to be 0.25, then 0.125, 0.0625. And the question always comes up, well, what do you set it at? How do you know whether stuff really travels long paths or not? And one way of answering that is to empirically have some kind of outcome variable, and then run the measure with all possible values of that parameter until you find the one that creates a result that correlates best with your outcome measure. And then you say, okay, now I know that, in fact, in this situation, in this context, it's only the short paths that matter. Once it gets past like 3 degrees, it doesn't happen. So that's like the result of Christakis and Fowler with the contagion of obesity. Their finding was that obesity is contagious, but it doesn't go any further than 3 links away. That after the 3rd link, there's just no effect of the first person's level of obesity on the 4th person down the line. What's missing in all that, what's wrong, is that those are just models. What we know in terms of the data often is how much stuff goes from me to you, and then how much stuff goes from you to Ja. But it doesn't we don't know whether it's the same thing that I gave you that you're passing on, or whether you're passing on some other stuff that you got from somewhere else. It takes a different level of data collection for that.
I think there was like something like, is there anything in like anything like a telephone game collection where you like give somebody this? I mean, I know we talked about like people sending on those packets to, who do you think would know this? Like, did you send it to like that broker?
Right.
But I didn't know if there was like a specific piece of information and you're supposed to pass it on to every single person in some way, shape, or form to be able to test, I guess, like what is the best way of communication amongst the...
There's not a lot of studies, but there are several like retweet studies so that we can see the tweet moving along. There is some qualitative work, some beautiful qualitative work by Gary Allen Fine, a sociologist, who studied stories that boys tell each other. Like, did you hear about the kid who put, what is that fizzy thing that you put in, Pop Rock? He put it in his Coke, and then he drank it, and then he exploded. And you watch that story as it goes from person to person. He followed like how it went, sort of higher status people, higher status, and how it got attributed later on as the original story of being to the high status kid, and then how it changed over time because people simplified certain things. The parts that didn't make sense, they dropped out, stuff like that. And then the other study I can think of that's like that is the anthropologist who picked an extended family and called them every Friday afternoon, called every single member of the family and said, "What have you heard?" And what news? And then they say, "And who did you hear it from?" And so she was able to confirm that bad news actually travels faster within families. She confirmed the stereotype that women are the ones that keep everybody informed, and that a lot of information gets to a guy and somehow just dies there, and key information is not passed on. Stuff like that.
Have they done like studies like that, but I guess with time? So like they ask somebody, "Hey, remember this?" and then try passing this on within a week, and like seeing how much, I guess, of the information that they were told to remember they can still pass on. So being able to see what kind of time increments they can still pass on.
I haven't seen that, but it's got to been done. It's just too interesting not to try.
Yeah, well, that's all I can think is that this has to be like something that has to be done.
Yeah.
Is the effect of the high status kid, for example,
Mm-hmm.
is that a pretty common effect where actors bring information to high status individuals and they disseminate it out and receive the benefit of that information?
Yes. It's been noticed in the boardroom and management settings, and it's also been noticed in the playground, and where the observer saw when the group first heard the story and knows that it was this kid that brought the story in from his cousin from this other town, and then in retellings of it, it is said that it was this other kid that brought that, and that kid was a higher status kid.
Now, the person that disseminates this story, are they seen to be the person that can tell the story they usually seem to be the person that can tell the story in the most similar way to which it was told to them, or are they seen to be the person that can make the story really juicy?
I think it's more like that, but
Okay.
I don't remember anything specific about that. But yeah, and I suspect that the people who are leaders, in informal leaders, are ones that tell stories well. I'm working on a series of studies right now in which we have real flow data because it's careers, and we know the full careers of people who started out. Their first job was at this place. I studied winemakers. Their first job, they graduated from UC Davis. Then they went to work for Mondavi. They spent a couple of years there. Then they went to Opus One, which is a high-end place. And they went to CME, and then they opened their own boutique winery. And that's a complete career, yeah.
Does that require a lot of field research?
It did. It did. My wife and I, and particularly I was very interested in how Sonoma was different from Napa, and so we interviewed winemakers up and down both valleys. Yep.
Let's take a field trip.
That's great. And I've also got data on basketball coaches and on soccer players moving from club to club. So those, you really know the flow. You know exactly who went where when. But you don't see them changing as a result. It's not your changing story. All right. So the UCINET way, of course, is to just measure something like reciprocity, and it gives you a measure. It's just 0.704. And you could then, if we had many different networks, we could correlate that with something. So that, for example, maybe the different networks are in different industries, and we expect more reciprocity in certain industries than others, and we could test that hypothesis. But it's just a measurement, and we use it in conjunction with other measurements of other networks. The ERGM approach not only gives you the kind of effect size that says there's a lot of reciprocity, but tells you that it's significant, it's more than you'd expect by chance, when we control for all the other things that are going on in this network. Okay. looking at my two question askers. So, since,
On status,
yes.
is that normally measured by interconnectedness, by betweenness, by centrality? How is status determined?
In
General.
in general, it's hugely variable. I would say that in organizational studies, it almost always is measured both by formal status, so it'll be some amalgam of rank, tenure in the organization, job type, and some kind of network variable, which will be a centrality-based thing. And people often ask the question, so who has influence around here? Who's got power? And just sort of sum up the number of responses to that.
So some kind of actual measure of prestige. Or,
Yeah. Why? What are you thinking about?
huh?
Huh? Am I thinking? I wasn't thinking. Yeah, you must be thinking about some study or something that you're doing. Okay. If it's secret, you don't have to share. Okay.
No, it's the idea that investors might be of higher status and be able to get information about smaller investment opportunities, and then that maybe potentially other low status investors bring those individuals' investment ideas, which they then disseminate in their network, and then that leads to greater co-investment now for that low status investor with the high status investor at a later date.
Very nice. Yeah. Yeah. So there, how would you measure status?
It's a good question. I mean, in our literature and in a lot of finance stuff, size is so correlated with everything that
Yeah.
it's hard to say just the biggest investment house has the most status, although that's probably a reasonable assumption.
Yeah.
You may have to then get to a size-controlled measure of possibly sentiment in press releases or kind of ratings that are out there. You know, if I look up news articles that talk about Anderson Horowitz, how positive is the sentiment versus Sequoia Capital, right? So something like that might help at least tease out some variation that isn't size related. But.
Yeah. That sounds good. Okay. So, let's look at some other kinds. So we talked about QAP and ERGM. We're going to drop the ERGM. We're going to look at other ways of playing with QAP. And then towards the end of the class, we're going to just start looking at network change in general, just correlational, but not necessarily based on QAP. So I think the first thing that I want to do, let me just call up my notes here, is I want to introduce you to something which is controversial. Well, let's do this. Let's do a QAP regression on the Paget data. Now, if you remember, to do QAP regressions, we've got to separate the matrices into separate data sets. So I could go to data and do unpack, and I can put in Paget, and it looks inside a Paget and says, oh yeah, there's a marriage matrix and a business matrix, and so it's going to separate those out. I press OK, and it says I created these data sets on your hard disk. Okay. Now let's regress those. So I'm going to press Control R, and the dependent variable is going to be PAG-B, and the independent variable is going to be PAG-M. PAG-M. And I run it. And it tells me an R square, and it tells me unstandardized coefficient for marriage, the standardized coefficient, which by the way is equal to the correlation coefficient, 0.372, and a p-value. Now, you may think, this is a little bit strange. How is it that we're predicting a dependent variable that is ones and zeros, and we're using essentially OLS here? Well, actually, it's not that strange. It's called a linear probability model. Statisticians argue about it, but many statisticians like it, actually. And the major objection to it is that the errors are not normally distributed, and so the p-values aren't correct. But because we're doing QAP, it handles the p-values in a way that is perfectly fine. So actually there's nothing wrong with predicting a binary dependent variable. However, stupid being as stupid is, there's just a lot of people that just can't accept that because they learned in graduate school that no, if it's a binary variable, I have to do logistic regression. It's just got to do it. So I've invented a logistic regression quap. It's something that is not in the literature yet. I haven't tried to publish it. I don't know if it works. It needs some simulation tests, but let's try it, okay? So cutting edge class, right? If you press Control L, well, not from WordPad, but if you're back in the menu here and you press Control L, it gets you to logistic regression quap, LR quap. The dependent variable is page B. The independent variable is page M. And to start with, we'll just, let's increase the number of permutations up to 5,000. And then we'll say, okay. And it gives us the usual output from logistic regression, including a pseudo R-square. It gives us the coefficients. Do people know what logistic regression is? Now that anybody not know what it is? Okay, so all right, so I don't have to explain that. So you know then that it's a linear model in predicting the log of the odds of the dependent variable. If we exponentiate these coefficients, we get these odds ratios, and they tell us how much change in the odds of y occur with 1 unit of change in m. So that 8.9, let's call it there, means that if you go from not having a marriage tie to having a marriage tie, the odds of having a business tie are multiplied by 9, or 8.9. Okay, so the odds of having a business tie, if you have a marriage tie, are multiplied by 8.9. And
It's multiplied.
yes, it's 9 times bigger. So, and that's highly significant. So it's cool, and that, it's nice to be able to have that interpretation to a coefficient. Now, what are the problems with logistic regression in this context? One is no one has done the simulation study to determine that when the null model is true, when you give it data where there is no relationship between the independent variable and the dependent, and you run it, you create simulated data and you run it 10,000 times, at the 0.05 level, it's supposed to only show up significant 5% of the time. And I don't know that that's the case. We can show that. In R, we could easily run that experiment. But the basic checks on this haven't been done. I have a pretty good feeling about it. I think it's works fine. But I just thought I'd let you know that this is not a technique that is already out there. But it sure beats explaining to people how you used a binary dependent variable. Okay. Now, this particular implementation has a lot of additional features. We're now going to switch to predicting. We're going to do longitudinal, and we're going to predict the CampNet data. But what I haven't told you about the CampNet data is that it's really Camp 92. If I display Camp 92, you see that there are 2 data sets in here, 2 matrices. One is called week 2, and the other is called week 3. What we've been calling CampNet is actually a dichotomization of week 3. And these are rank orders. So in week 3, Holly is saying that Pam was her number 1 person and Don was her number 2 person. So what we're going to do is dichotomize these two matrices so that they're 1s and 0s, because we want to play with that logistic regression thing. So I'm going to close this and slow me down if necessary. I go to transform, I go to dichotomize. The input data set is Camp 92. The output's going to be called Camp 92 greater than 0, but that's not actually, we're going to change that. We need a dichotomization rule, and because small values here mean stronger ties, I'm going to dichotomize it like this. If the original matrix value is greater than, is smaller than, is less than or equal to 3, then make it a tie. Otherwise, make it 0. Now, what does that do? All I'm doing is saying, I want to create a tie when somebody says, oh, this is one of my top 3 interactors. Okay, and a non-tie otherwise. So, and do I want this Camp 92 less than or equal to 3? I guess so. It's ugly, but let's let it go. So there it's dichotomized both matrices using the same rule. Now I'm going to split them apart. I'm going to unpack them. So I data unpack. It's Camp 92 underscore less than or equal to underscore 3. And the results are going to be called week 2 and week 3. That's fine with me. So I run it. It says it's created week 2 and week 3. And now I'm going to use logistic regression to predict week 3 from week 2, which, ought to work. I press Control L. Oh, actually, if you want to find out where it is in the menu, you can go to Tools, Testing Hypotheses, Dyadic, Logistic Regression. Notice the word beta in there. Also, something, this is very technical, but if you read the Psychometrica paper on this kind of stuff, it turns out that the way permutation tests run is that you do the observed regression, and then you permute one of the matrices, and then you re-regress them, and you keep track of all the betas, and then you count up at the end of that how many of those 10,000 betas that you got by randomly permuting things were as large as the beta in your real regression. It turns out if you don't track betas, but instead track what are called pivotal statistics, such as t-statistics, it works better. This program actually doesn't have that implemented, so it doesn't matter what you choose here, it always gives you the same thing. But in the future, you should always use t-statistics here. All right, so we're going to predict week 3, it's an underscore, from week 2, and we're assuming that we can predict. And indeed, the t-statistic, which it doesn't even really use internally for significance, is really high. It's highly significant. And the odds of having a tie in week 3, if there was a tie in week 2, are 26 times higher than if there was no tie in week 2. Okay, so it's like it really has a big impact on week 3 ties. Fine, that's just a baseline model. I just wanted to get that out of the way. Because we've looked at this data, and actually, let's open NetDraw. Do you guys have this version with the QD? No?
Yes.
No. All right. I just like to see who's up on things and who isn't. So at some point you should probably download the latest version of UCINET. Nope. You just you download it, install it. Don't uninstall the old one, and the registration code will automatically be there. So I'll run it with the old button, so it's similar to what you've got, and then I open camp 92 underscore less than or equal to underscore 3. This is the dichotomized version for both matrices. And let's bring in the genders of the people. So I'm going to do the open with an A button. Open with an A. And I know that that's in a file called camp.attr. And even though the network data is over time, the attribute data isn't, because their genders didn't change over the week, right? It takes a lot longer to change genders. And if we go over to nodes then, over on the far right, I'm going to choose gender, and then I'm going to press the color button. And this has been happening for 10 years now, but I've never seen it, when you use gender, I've never seen it not coded blue for boys and red for girls. And I swear, there's no code in there that looks at the names or anything like that. It just comes out this way every time. So this is week 2 that we're looking at. I can tell because if I go over to the Rels tab, week 2 is checked off. And you can see that in week 2, it was basically 2 groups, and gender was a big part of this. If we press the down button here, the DN button, it switches us to week 3. And if I were to press the lightning bolt, I could see that, well, now it's actually split into 3 groups, but gender is still an important factor. And I could go back up to the other one. It's annoying that we can't see it beautifully both ways. I've shown you this before, but I'll show you one more time. If you go up to Properties, choose Lines, choose Multi-Relation Selection. So Properties, Lines, Multi-Relation Selection. You could press Next, and you see week 3, and press Next again. That goes back to week 2, and notice that it's running the lightning bolt each time. So you can see how it changes. So anyway, what I'm thinking is gender is a big part of this. We should be able to predict ties based on gender. And so if I go back to UCINET and I press Control L, there is this cool thing that you can do. You've got week 3 as the dependent variable. You've got week 2 as an independent variable. Down here, you can enter a data set that has node attributes, such as gender. I could type in camp attr. And down below that, there's a drop-down box now that has all the attributes that were contained in camp attr. We could take gender as one of them, and we can build what I call an effect. And the effect is homophily. And categorical, because gender is categorical. And then if you press the button called Add, it adds it up here. Now, what is it actually doing? I'm going to cancel this and display you see how the most recently created file is called gender homophily categorical. What it did is, when I chose that effect, is that it created a data set to throw into the regression. And if we looked at that data set, all it is a bunch of ones if it's a tie from a woman to a woman, and a bunch of ones if it's a tie from a man to a man, and zeros if it's a tie between genders. And you've seen me do that mechanically before. The way we did that before was we went to close here, we went to data, we chose attribute to matrix, we put in camp ATTR, we chose gender as our variable, it automatically called it same gender, we chose exact matches, we run it, and it creates that matrix. But instead of doing it by hand, we can just go to Control L here. We put in camp ATTR as our data set, we choose gender as our attribute, and we choose homophily, and so it creates that matrix for us. We could also, while we're here, do the same thing for role. We could put in role homophily, which in this data set, of course, is instructors versus participants. So now we're saying we think that the likelihood of creating a tie in week 3 is a function of whether or not people are the same gender, whether or not they're the same role, and as a control with putting in the week 2 social structure, which in a way gives us the change in the network. We want to see whether new ties that are being added and old ties being removed is a function of gender and role.
So what do you do with data R? Because 2 of these are undirected now at this point.
2 of the, oh yeah. Why do you say data R? Data R. Oh, I see, yeah. You definitely want it to be non-symmetric because there are some non-symmetric data here. Yeah. You would only use that if everything was symmetric. Okay. And so, yes.
Can we build an interaction of gender and role?
Not yet. But, well, I'll show you how. It's only one step. So it's just not in that screen, but we can do it. Let me just see what the results were, though. It looks to me like role homophily really isn't the issue. But gender is. Okay, so gender is significant. And if we look at the odds here, it's saying that if 2 people are the same gender, the odds of having a tie in week 3 are multiplied by 5, or 4.9 to be exact. And of course, if they had a tie in week 2, the odds of having a tie in week 3 are multiplied by 17, as compared to not having a tie in week 2. Now, interaction. Okay, so the cool thing about the very primitive way that that this works, let me Control L again, is when we created these effects, it just created matrices and put them in the hard disk. So now I could interact those, and I could close this, transform, make interaction term for regression. Yeah, it's even a full sentence, you know. And I could put in as one of the data sets, I could put in that same gender thing, and as the other data set, oh wait, I think I have to choose them one at a time, don't I? And then the other one is the gender one. It offers to mean center things. So let's see what it actually creates out of all this. I'm a little confused because I thought it would also print out like the mean-centered, each one of these variables plus the interaction term that it computed after mean-centering them. Let's display and see what actually happened. Oh, it does, yeah, okay. So it's got there's the interaction term, which is the role against the gender. It's got the role mean-centered, and it's got the gender mean-centered. And so now we could go back to our Control L, get rid of the unmean-centered versions, and of course I'm assuming that you all know what we're doing here. It's got nothing to do with networks, it's just ordinary regression and testing moderation hypotheses. Throw all of those in and run it. And the interaction was not significant in this case, but it was a good idea. Gender comes through though. Gender is just a very significant patterner of ties in this network. So, how are we feeling? No problems? Questions about how you might use this?
If you don't do mean center, will it a difference result?
If you don't mean center, the significance of the interaction term will be exactly the same. It will not change. The conditional effects, what people mistakenly call the main effects of gender and role, they will be different and will be hard to interpret. And the reason is that they will tell you the effect of gender on week 3 ties when role is 0. And that isn't even possible in these data. Oh, actually it is. Sorry, in these data they are. Because it's role, it's whether or not you're the same role or not.
So we don't need to mean center.
So actually, you don't need to be center for, these are 2 categorical variables,
Yes.
and you in no case do you ever have to mean center if you're just going to interpret the results of the interaction. People for some reason don't know this, but you can test it yourself by running the regression, mean centering your variables, not mean centering it, and comparing them in Stata, in R. You'll find no difference.
But only the significant variable not change. The coefficient will change.
The coefficient for the interaction term will not change, but for the 2 individual effects, properly called conditional effects, they will change. You could get reverse coefficients. You get negatives when they were positive before, and it can be very confusing.
But the significant are all not change.
The significance of those will change as well. The only one that will not change is the interaction term, which is actually the one that you're testing. So it's okay. So I'm guessing that we just need a break. Should we come back in an hour? Okay. Let's take a little break, and then let's do a little dance, and then we're going to do some other kinds of longitudinal stuff.
The stochastic power is why does the lagged variable for obesity take care of homophily?
I don't understand.
So let's see. I had it over. So this is stochastic power. You guess the time lag and the variable, useful lag independent variable, and all the statistical.
No, I just paper.
Oh, yeah. So, if there's an association between, say, similarity of weight and whether or not you're friends, how do you know that which direction the causality is? It could be that fat people choose other fat people to be friends, and that's homophily. They're ruling out homophily by saying, but we're measuring the friendship before the weight. So we know that it's the fact that we're friends is influencing each other's weight.
But, so this was height. And I joined the basketball team because I was a 7'7". Wouldn't that also say that I became tall?
Well, you know the paper, obviously, that talks about that.
No, I don't.
Oh, well, there's a paper which
Is that really?
they try to make fun of these guys by using
using that
examples just like
But
that.
this wouldn't that, okay, so it's just, it's
Um,
not really a thing.
Speaking of which, though,
Yeah.
we started hanging out, and now he eats a lot more pizza.
Now we get along. And also,
Yeah.
I sent you 5 papers about using status.
Oh, I haven't read
Sure.
it. You're like, what did you do?
I don't think it actually counts until the professor answers them.
What was
I'm just listening.
What is the other one? What's the one that it
I
was,
wanted to tell you.
yeah, sorry.
No, can I say?
Or, you know.
Sorry.
Are we eating pizza today?
Yes, I wanted to make sure of that.
Okay, yeah. What's the other one? Because when so how,
I don't know. Look up criticism of Christakis and Fowler. That should probably find it. But they prove, using the same methods, that something ridiculous,
like that?
like that height is contagious.
Yeah, you would.
And age, too.
When
They,
it would naturally really.
yeah.
I have a quick question. Hypothetical networks, do people do those? Like, let's say, sorry, I'm like fascinated by knowledge and like passing it to other people. I guess in a more applied public health means, HIV knowledge, okay, and like age being a variable. So asking people, what would you tell somebody of like young age about the disease of HIV? What would you tell somebody of like adolescent age about HIV? What would you tell an adult about HIV? What would you tell a peer about HIV? What would you tell if you're male? What would you tell a female about HIV? If you're, I guess I'm assuming that you're mid-age. What would you tell an elder about HIV? Do you ever see those? I guess like ego networks that like maybe measure how much information is going from person to person, and therefore being able to measure age as a variable and show each one. I guess would be like those from maybe. I don't know.
Yeah, I think that ends up being, you do that sort of not in a networky way. You'd reduce it to a standard sort of statistical thing that, in fact,
So it wouldn't even be about networks anymore. It would just be like statistics.
yeah, I think it's like your gender affects which gender you tell X thing to.
Yeah.
Yeah.
Okay.
How do I take my coffee?
Reverse.
What's the same? What can I expect to have?
That's not, first of all, that's not coffee.
It's not coffee.
No,
It smells like coffee.
it's not coffee. It's not water.
Oh, sounds like an Americano.
It's totally disgusting.
Totally disgusting.
Very disgusting. It tastes bad
Why are you drinking?
because it's sweet.
Totally disgusting.
No, are different.
You are different. I will give you that.
Bring to my ass. I went to the conference yesterday. I went to a conference in it's like, okay. And looking at all of the cool people from Harvard and Stanford and Wharton, which is like, I want to be there so bad.
That's you in the future.
started talking with this when someone was younger and they were doing something, and I thought they could use social networks as a part of their cities. And they got excited. I said, we'll do what?
Stanford has a big program about social networks, their history. And like,
Oh, okay. They are in marketing. They don't know.
yeah, marketers. That's different.
Yeah, they don't know anything. So I was like,
They don't
I
know
can help you with that.
That's so true. They don't know anything. That's darn dirty marketers. Hey, that's my copy.
Yeah, you guys want
Where was your conference?
Florida. San
Were you down in
Clearwater.
Were you down in my hometown 2 weeks ago with Emily?
That that's
You didn't like it?
I hate it.
I get you.
I hated everything about it.
That's very sweet.
One small place in the middle of nowhere, and the fanciest restaurant that they had was somehow
As if R was
access.
really a program.
It was like this place for barbecue and stuff, and they said all the football people here is so fancy and stuff. It was not.
No,
It was
it's not.
really, really bad.
Why would you go to a fancy? Why would a fancy barbecue restaurant exist?
She did not think that was funny.
Right? What is Mrs. Pitts?
You're so nice to me.
It's acting like you're from there. You're not from there. You don't have any of that.
18 years in Mississippi.
And you didn't learn anything.
I didn't learn anything.
You didn't.
I didn't know. Next time I
You, 18 years you.
I used to anyway.
Okay, 19 years you stayed there,
Yeah.
and you possess none of the attributes of people from there. So I don't know. Do you
I think I do.
like what?
I mean, like, I don't think it's on me to defend myself.
I don't think there's anything there that
Okay,
It's really sweet.
let's switch gears a little bit, but not too much.
No, I'm totally.
If you stop saying people that you're from there, no one would guess that.
One of the most used concepts in network analysis is, I wish I could close this window, is structural holes. And we study structural holes next week. And the week after that, well, we have spring break, but the week after that, then we have 2 weeks of centrality. And these are the big concepts in the field and the ones that do most of the work in terms of predicting outcomes, such as performance in organizations. But I'm going to preview that a little bit today. I just can't figure out how. UCINET. Killed again. It's like a video game. You just can't get to level 2. I just keep getting killed. Alright. So, suppose we run a classic kind of analysis in which we have performance, such as supervisor's evaluation, and we have characteristics of the individual and network characteristics such as structural holes, and we're going to do a prediction. Well, actually, I'm going to use centrality here. So let's run centrality. We go to network. We go to centrality and power. And you can just tell that this is an important area in the field. I mean, look at all the different measures available in UCINET alone. And we're going to go up to multiple measures. Oops. And we're going to put in CampNet, which we now know to be week 3, by the way. And I'm going to pretend that CampNet is undirected, that is, that it's symmetric. So I'm going to press the undirected button here. And here are a bunch of different measures that it's going to compute. You could turn some of them off. I'm not going to bother. We'll go into detail of explaining each of these measures later on. Let me see if this looks right. It does. Okay, so we now have a bunch of measures of centrality of each person, including betweenness centrality and eigenvector centrality, which are two very popular measures. Now, the way we would normally use this is we would immediately transfer this to our stat package, where we have other data on these people, and we'd have, say, their performance, and we predict that people who have high centrality would be better performers. Or the opposite, we might be interested in how do people get into these positions of high centrality. Maybe it's personality characteristics, and we predict that. Now, in journals, we get away with doing that, but I want to point out a problem with doing that. And the way I'm going to point it out is I'm going to open CampNet in NetDraw. So let's open CampNet in NetDraw. I open, and then I go the open with a U, because we're going to open a UCINET file. And we're going to put in CampNet. And now I'm going to pull in with an open with an A, I'm going to bring in the centrality measures that I just calculated. And I forget what they're called, so I'm going to press the little button here. And it turns out they're called CampNet-Cent. CampNet centrality measures. So I open it. It's great. I now go over to the Nodes tab on the far right. I do the drop-down menu, and I see all these measures of centrality, and I'm going to choose betweenness because I've heard of betweenness before. It's a famous one. And then I'm going to check off the bottom, at the bottom right here, I'm going to check off the size button so that it's going to size the nodes by betweenness. Now, you notice that betweenness is not randomly distributed across these nodes. All the high betweenness nodes are connected to each other. And here's a great example over here where these are two high betweenness nodes and they're connected to someone that's a little bit less, someone that's a little bit less, a little bit less, 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 less. There's a sort of gradation away. That's called autocorrelation. That means that John's centrality, John's betweenness, is not independent of the betweenness of his friends. There's a general principle that if you are highly between, that if you're connected to high betweenness people, you will also have high betweenness. It's not a perfect correlation, but it's there. Same thing, I'm going to go up to nodes over here, do the drop-down menu, choose eigenvector centrality. Eigenvector is this cool measure that says my centrality is proportional to the sum of the centralities of the people I'm connected to. And notice again the autocorrelation. All the big ones are connected to each other. And as you move to the left here, they get smaller and smaller and smaller. And all the people with low eigenvector centrality are connected to each other. So you know then the observations are not independent. So if I go back to UCINET and I display my centrality CampNet-Cent thing, and suppose I had a 10th column here, which is performance. When I correlate performance with betweenness or performance with eigenvector centrality, I know that really these observations aren't independent of each other, these cases. Even though it's not dyadic, there's an issue here. The best way to solve that, well, there's a few things you could do. At the very least, if you're running this in a regular stats package, I would at least use robust standard errors, and I would use bootstrapping to calculate the standard errors. Those improve things, but they don't quite do away with the autocorrelation problem. The only thing that will really do it is the permutation approach. We don't call it QAP because QAP is specific to those dyadic cases. But it is a permutation-based thing. And the way it works is, let's say I'm correlating eigenvector with betweenness. I run the actual correlation, and then I randomly permute the rows of the eigenvector, correlate it with betweenness, and I do this 10,000 times, and I count the number of times in which the correlation is as large as the real correlation. We can do this in UCINET. I'm going to show you how. I think I want to have an actual measure of, well, you know what? Instead of making these the independent variables, let's make them the dependent variables, and we're going to predict centrality from gender. Let's find out if women are really more central than men, which I think would fit stereotypes. So I'm going to close this. I go to Tools, Testing, Node Level. We're not doing dyadic anymore, so we're doing node level regression, or Control-Alt-R. And this is one of the older programs in UCINET, so its interface is kind of ugly. The data set is, for the dependent variable, is CampNet-Cent. Those are all the different centrality measures. By default, it says I'm going to pick the first variable in that as my dependent variable. But if you press the little L button, it shows you what is in that data set, and you can decide that, no, it's eigenvector that I'm trying to predict. That particular measure is centrality. And again, when we get to the eigenvector, I'll explain it in detail, but loosely it's a measure of the extent to which you're connected to people who are well connected themselves. The independent data set is going to be CampATTR, where we have some basic data on the people, the campers. I press that L button again, and I can choose gender. Actually, I could choose, let's choose gender and role. Let me do that again. Now, if I choose gender and highlight them both, how about that? I press OK. And you see what it did is that under independent column numbers, it just said, oh, column numbers 1 and 2. Pretty basic. So we run this. Correlation matrices, the inverse of the correlation matrix is a bunch of junk. The R square, and now here we have our usual regression output. The gender coefficient, standardized coefficient, and the p-value is not significant. It's gigantic. It's 0.35. Reading this is a little bit tricky because the role variable is negatively related. So the question that we really want to know is, in the randomly permuted variables, how often did we get a regression coefficient as low as 0.081? So we look at the proportion as small, which is 0.085. Still not significant. So these are both one-tailed tests. Here is actually the two-tailed test. And this should match quite well with a stat package, assuming that the data fit the conditions of the classical test, which I'm claiming they don't because of the autocorrelation. But we could test this, and in fact, I think we should. So I'm going to run this in Stata. I guess I won't close that window because we're going to need to look at it again. I'm going to go to the CLI because I'm comfortable there. I'm going to say Excel. Join calls CampNet-Cent and CampATTR. So what that says is, first, join two different data sets to be additional columns. have multiple variables. Some of the variables are centrality measures, some of the variables are things that we already knew about the people. Join them together into one data set, and then open that in Excel. Right, so here it is in Excel. I think I'm going to add in a variable name for ID here. I'll just put in ID. And then I'm going to highlight everything, Control C it, and I'm going to start up Stata. Where is my Stata? There it is. And I'm going to go to Data, Data Editor. I'm going to paste it in. The first row are variable names. I close this. And now I run a regression. I regress. Let's see, we were predicting eigenvector as a function of role and gender. So I run the regression. The R-square is 0.1341. What was it when we ran it in UCINET? The R-square is 0.1341. It's the same value. So clearly it's the same kind of regression. The only difference between Stata and UCINET is how we're getting the significance values. Then, what's the p-value for gender? 0.671, not significant. And for gender, it's 0.349. Oh, actually, this is two-tailed over in Stata land. So proportion is extreme. 0.693. We got 0.671. They're very similar. For role, the coefficient is minus 0.0811. We get the same coefficient. What's the significance? Well, the two-tailed significance is 0.085, and here it's 0.157. That's a little bit different. Had those data conformed perfectly to the classical test, it's a random sample, the data are not autocorrelated, the results from from the permutation test and from the Stata would be virtually identical, indistinguishable. But in this case, the story is the same either way. So, you know, my feeling is in reporting these things, I normally go with the conventional one like Stata, and I point out in a footnote that there is some autocorrelation problem, but we also ran this in using a permutation test, and we got the same results. Yeah.
I don't regularly use Stata, but do you need to declare something for robust in there? Or?
Yeah. Yeah, so we could do that. Smart thinking. Robust. I know, it's just so difficult. So for role, it's 0.09. And here it was 0.17. No, I think that's closer than it was, right? Yeah, it's closer. But anyway, we could also do a bootstrap, I think. I can't remember how you do it. Does anybody know? It's something like bootstrap regress? Anyway, the bootstrap will come even closer. So, what I'm saying is, if you really want to get it right, do that regression that involves a node-level network variable, use the permutation tests, but in practice, most people aren't aware that there's any issues with that, so you could just run the standard one. But I would run the robust standard errors, at least. Whew, questions? Yes? No, you can't compute centrality or any of those things in Stata. It just tests things, but it doesn't measure stuff. You think you can?
Well, my TA my RA sent me this code. And
Oh,
Yeah, someone wrote
so
a package.
I
sure,
just,
okay.
And he said, check this and see if it's the same in UCINET as what you can do in.
oh, okay, yeah. Because Stata, like R is kind of a programming language, you can program anything you want in it. And you could make it do it. There's going to be a lot of things that in R are just going to be, or in Stata are just going to be too slow because they're higher level languages. But something simple like degree centrality, you could calculate that in Stata if you wanted to. I wouldn't bother though. Okay. So now let's switch gears. I want to start talking about just change in general and not so much statistically evaluating the change. Although you should be aware of the Sienna program, which is fantastic for that. And Sienna, you can feed it longitudinal network data, so you've got multiple, slices of time, and you can feed it attributes of the people, which may be time dependent as well. So the classic example is you've got the network changing over time, and you've got smoking behavior changing over time, and you want the program to work out the endogeneity issues of, like, we know that smokers seek out other smokers to be friends, but we also know that if you have friends that are smokers, you may adopt that smoking behavior, and it kind of sorts out all of that stuff. So Sienna is really powerful for that kind of stuff. What I'm going to do is a lot simpler, though. I don't need Sienna for it. PowerPoint. That one. Okay. So I wish I had these data so that we could play with them, but I don't have them, so we just have to look at the slides. But this data set is an ecosystem. It's a marine ecosystem, and the nodes are species, and the tie is who eats whom. And actually the tie is carbon flow. So there's carbon flow from you to me if I eat you, right? And the data are collected at 4 time periods, so 4 seasons. And we can look at the density. Now, let's just try and figure out what the density means. Density, as you know, is the number of ties in the network divided by the number possible. So, what is density in a food web? Yeah, that's right. And it's not about like how much you eat, it's how many different species you eat. It's like, I eat that species, I eat that species. It's sort of, well, it's not omnivory exactly, but it's eating a variety of species. So an obvious thing to do is to take a statistic like density and simply measure the density of the network over time. And you can see that if you did that here, the density of the network declines as it gets cold. It's almost like this ecosystem is kind of contracting or something. There are fewer species around to be eaten, and so there's just less available. We're not going to run this exercise, but I'm going to post these slides, and you can run them.
So Steve, is density calculated? So look at there's 3 types, 3 species,
Yeah.
and each one only eats one other, not multiplication. So is the density 1/3?
Density is going to be so who eats whom in this one? Is it each one species?
3 of us are, and so it was like, I'm connected to Monica, Monica connected to her, and she's connected to me.
Oh, a cycle. That's
So
a little
what's
weird,
the-
but
well,
yeah, okay.
I'm just
Yeah.
trying to figure out how the is it.
So that, because it's directed, there's 3 actual ties there that you mentioned, but there's 6 possible.
Okay.
So it would be 1/2.
Okay.
Now, density is awfully simple, but let's look at a more complex way of describing the network as a whole. And this lets me introduce a whole area that is useful to know about. It's called the triad census. And what it means is that we can break down any network into a series of little triads, and we can count them up. So for example, one possible triad, which is labeled 003, is the triad in which none of the points have ties with each other. Okay? That's actually the most common kind of triad in almost any network. Take 3 people at random, they have no ties with each other, unless it's a really small network. The naming convention is MAN, mutuals, asymmetrics, and nulls. There are no mutual ties here. A mutual tie is one that has a double-headed arrow like that. That's a mutual. So you see that the name for this triad starts with a 1. There's one mutual. There are no asymmetric ties. It's a 0 there. This is an asymmetric tie. And so this triad has a 1 right there. And nulls mean that there's no tie. So this one is 003 because there are 3 null ties and no of the other kind. This is 012 because there's no mutuals, there is 1 asymmetric, and there are 2 nulls. Onward down the line, here's 300. There are 3 mutual ties and nothing, no asymmetrics and no nulls. So there are 16 possible kinds of triads, and we could count them all. And so for CampNet, I did that, and you can see that 345 of the triads are the all nulls, which is normal. This profile here is like a signature. Every network has its own signature, and some networks have more similar signatures to each other than others, right? So we can have networks that have big spikes down here. This one has very low numbers here, but it's got big spikes over here. If we apply this to the Chesapeake Bay ecosystem, we've got the network at 3 points in time. We can count up all of the triads of every kind, and we can compare the profiles. And actually, you know, since it's the same network and it's the same kind of tie, they all look alike. It's the same profile practically. Although there are differences. Like look at the 102. In spring and summer and fall, there's not very many, but there's a whole lot more in winter. Now what is the 012? It's this one. So it's one that's pretty sparse. There's no mutuals. There's a lot of nulls. So we're seeing a lot of nulls going on. That kind of goes along with lowering of density. Look at the next one. 021D has the opposite pattern. It goes down as we go towards winter. What is the 021D? That's this pattern. That's a species that is eating these 2 prey species here. Now, it's hard to quite get the pattern. Oh, here's another one that's declining over time here, 021Cs. One way to understand this is to represent this visually. The technique that I chose is correspondence analysis. Correspondence analysis is a technique which, given a rectangular matrix where the rows are different from the columns, it places columns next to each other, like it'll put spring and summer next to each other, if their profiles are highly correlated. And it'll place 2 triads next to each other if their row profiles are really similar, highly correlated. And it'll place a triad next to a season if that triad happens to have very large numbers for that season, given that in general this has big numbers, and given that in general this column has big numbers. It's sort of residual from expected values based on the overall numbers. So what do we get when we look at that picture? Well, first thing we get is that here's spring, summer, fall, and winter. We see a kind of, not linear movement, but a kind of monotonic movement. Start at spring, the most similar season to spring is summer, and the most similar one to summer is fall, and then the next one is winter, which is a little bit more different from all the others. So there's almost a progression over time. Now, which triads are associated with which seasons? Well, over here on the right, if you notice, all the names of the triads begin with zeros. These are all zero beginning ones. And if you remember what a zero beginning one means, is that that first one is a mutual. So in those seasons, no species eats the other species in a reciprocal manner, which you may think is really weird. Like, are there any species in which, like, the lion eats the tiger and the tiger eats the lion? There are. There are plenty of species that do that. Particularly, it's the adult of one species eating the young of the other, right? That kind of thing happens.
Lizards and birds.
Lizards and birds, okay. I didn't know that.
It's the extent of my knowledge.
Okay. So you notice that in these seasons, we don't have much mutuality going on. As we go over to winter, that's where all the triads that have a first digit that is non-zero, even a 2 over here, it means that we're getting towards triads where there are mutuals. This is a complete, I'm just making this up, but it's as if this, again, the system has contracted, there's fewer species out there, and they're eating each other. Brittany, who actually knows about these things, do you have any comment on that?
Well, I just had a general question. So with remind me again with the mutuals.
So the mutual is a pair of species that are actually eating each other.
Okay. The biologist in me wants to ask what species are actually there, because if you understand the differerences in species, it would explain a lot of this.
Yes, I'm sure.
So I could see this pattern though, because a lot of species, they don't necessarily overwinter, especially in the Chesapeake region, and so you end up with that right there.
Yeah.
The biology definitely supports it.
That's good to know. And I mean, we're seeing a definite pattern of change over season. I mean, it's like we don't see it in these seasons. We do see it in this season over here. I should also point out, though, that because of the difficulty of gathering highly granular data, some of the species, particularly for the really small species, are collapsed together in groups. So they're called compartments. And so actually what looks like a species eating itself is really one member of the compartment eating another member of the same compartment. So, but this tells a better story.
There's kind of a short tie, the weak ties argument in here where the 2 mutual is much more likely to have a asymmetric and not a null, if you look at the table.
That is true, yes. And so, okay. So when you've got a mutual, let's find, like here's a mutual with some asymmetrics. And you're saying that...
So if you look at the 210 and the 201
Mm-hmm.
In the table,
Those two?
yes,
Yeah.
you'll see that the 210 I think is much more likely than the 201.
Mm-hmm. Okay.
And that
That is consistent with this weak tie, which unfortunately the substantive explanation for weak tie has to do with like intimacy and things like that, and I'm not seeing that happening here. Like the normal explanation here would be that this species is actually introducing this species to this species, So, but anyway.
The mutual should be 2 species eat each other, right?
Yes.
Not in the unspecies they eat each other.
No, there's no reflexive ties here, so this is not. There may happen, but no, I don't have recorded that they're eating themselves, like their brother or their own children. which we know happens.
I have a quick question
Yeah.
actually about the correspondence analysis.
Yeah.
This is just based on the visual. It looks very similar to what was run, it's like a PCA analysis. Kind of, okay. same
It's very
premise.
similar. The only thing about the the PCA analysis, you're probably thinking of like what would be, it'd be a vector model, and it's like you've got one dimension is the first principal component, the other is second,
Yeah.
and then it's sort of loadings on those. And this is not a vector model, this is a point model, so that it's whether or not two are near each other, and the actual axes are arbitrary.
Okay.
So in a PCA analysis, there's a center point, and you could draw a vector to each point, and if the angle between the two vectors is small, it means the correlation is large between those two.
Okay.
But it's the same general idea.
This is more like multi-dimensional scaling.
This is very much like multidimensional scaling. What it is two-mode multidimensional scaling as opposed to one mode. Multidimensional scaling needed a matrix, an input matrix that had triad by triad or species by species, but not both. Okay, so let's look at another one. Have we talked about the South Pole here? Good, okay. Let me introduce the concept of core peripheryness. And this is a concept at the level of the whole network, and it's a way of characterizing the entire network. The network on the left is what we would call, what I call a clumpy network. Some people call it a cliquey network, some people call it a caveman network, some people call it a small world network. The characteristic is that it's got these little clumps of density, but that overall it's not got a lot of cohesion. There's few ties between clumps, but lots of ties within clumps. The network on the right is a core periphery structure. It's sort of a structure that has just one clump, and that clump is the core. And if you notice, everybody in the core is connected to everybody else in the core, and the core is also connected to the periphery. But what's key is that the periphery is not connected to each other. If the periphery were connected to each other, that would bring us over here to the clumpy network. And there are big differences between these two networks in lots of different settings. So, for example, in terms, if this is in a management setting, and we ask people about their sense of identification with the organization and with the group, there's a strong tendency for the purple people here to identify with purple people and not with the group as a whole. Whereas over here, the green people, even the green people who are peripheral, tend to identify with the group as a whole because there's a sort of focus there. We know that for certain tasks, the core periphery structures perform better than the clumpy structures. We know that morale tends to be higher in the core periphery structure than it is in the clumpy one. There's a lot of differences. I'll give you one example here. And the key thing that I want to point out is that we can measure the core peripheryness of the network. I'll explain how we do that in a later class, but if you notice, here's the measure. The CP value for this one is 0.12. The CP value for this one is 0.85. It's clearly identifying that this has got more core peripheryness than that one does. Now here's some data collected by Jeff Johnson. And what I'm going to claim about this is very anecdotal, but it's great pedagogically. So he went down to the South Pole. He actually did the whole training thing. And in the South Pole, they drop you off in March and they pick you up in October. And you're there for 8 months. And you're pretty well stuck there. Today they have lots of email to the outside world, but it used to be you had very little communication with the outside world. And so it was an ideal setting for studying small groups. They also have a physician at the station, and the physician gives every single person a complete physical every month and will also administer questionnaires for you, like network questionnaires. So we can measure the network of friendships and other kinds of networks every single month of the 8 months that they're down there. And for each of those networks, we can measure the core peripheryness of the network. So this picture up here, this line up here, is the core peripheryness of the network. So when they started out, they had a structure that looked like this, very core periphery. And in particular, there was one task leader that was very clear, and there were a number of sort of expressive leaders that kind of held things together. And you notice that over time, the core peripheryness starts going down. And in fact, it took a big slide here. And for this particular year, what happened is that one of those expressive leaders that was in the core here was sexually harassed by somebody. And you can't escape people there. And what she did is she kind of temporarily escaped. So she shifted her shifts so that she was working when other people were sleeping and stuff like that. And then people started taking sides on, did it happen, did it not happen, who's right? And the network turned into this over here. There are factions. And of course, when that happens, the core peripheryness takes a big dive. What's interesting is that there was also a standardized measure of group morale. And it seems like group morale follows the network structure, lagged by a couple of months. So when the network structure does this in terms of core peripheryness, morale does that a couple of months later. When core peripheryness takes a deep dive, then morale takes a deep dive. When things start improving in terms of core peripheryness, morale starts improving. They kind of mirror each other, which is a beautiful story for any structuralist who thinks that structure comes first and then everything else sort of follows. There are clear holes in this. One is that when you go to the South Pole, it's fun at first, and then it ceases to be fun, until you know that the end is coming, and then things get better. And sort of everything goes to pot, and you can't really tell the causality in anything. He has since then, though, studied 11 other sites, different South Pole and North Pole ones, and so he's got a lot more data, and there's some interesting conclusions to be drawn from it. But I just want to point out that we can take a measure of a network as a whole and measure it over time, and then try to relate that to something else. And also, by the way, team performance was also measured in this, and team performance was declining rapidly as well. It could be just the morale, but it could also be that it lacks that cohesive structure, lacks that clear leadership. When you have a group like a network like this, there might be a purple leader, there might be a black leader, and there might be a green leader, and they may not agree with each other, and it could be very difficult to get work done. But it's much easier to get work done in a core periphery structure. Okay, now let's look at individual changes. So we're going to take properties of the individual, for example, some kind of measure of their social capital, and look at how it changes over time, and then see how that has consequences for the person over time. And here I will depart from the slides, and let's do this in UCINET, because it's kind of fun. So go to UCINET, and let's display the Newcomb fraternity data, which is NewFrat. So display NewFrat. I'm in the CLI, by the way. So if I display NewFrat, and hit enter, you'll see that you get 15 different matrices, one for each week. And as I explained last week, these are rank orders, and a 1 means that's the person that they like the most, and a 17 or a 16 is the person that they like the least. Now let's dichotomize this for simplicity. So I want to dichotomize that in such a way that I'm going to take the top 3 ties for each person. So I'm going to say D equals dichotomize new frat less than or equal to 3. That says go find a data set called new frat, and for every value that is less than or equal to 3, call it a 1, and otherwise call it a 0, and put the result in a new data set called D. So I hit enter, it creates D. If I display D, I see that it's converted all of my matrices to 0s and 1s, and a 1 means that the person is a top 3 friend. Okay, now I'm going to calculate the number of friends that each person has. Now, just looking at this matrix here in week 0, how do you calculate the number of friends that a person has?
Column. Not actually a column.
Yes, just sum the column, right? So person 1 here has 2 friends, or 2 people that consider them among their top 3 friends. Person 3 has 1 friend. Person 17 has a lot of friends. A lot of people put them in their top 3. So we're just going to take the column sums. Actually, there's a convenient routine. I'm going to call it deg equals in degree. In degree is the number of ties coming into a person of the data set called D. Okay? But all it's doing is taking column sums. And now I can display deg. Oops. Let me go back to the program I was working with. Now, how do we interpret what we got? The rows are people. There's 17 people in this fraternity. There are 14 weeks. No, there are 15 weeks. 0 through 15, but there's no 9th week. So there's 15 of those. Notice the patterns. 17 was popular on week 0, popular on week 1, is just plain popular all along. Person 16, not so popular all along. Person 10, great start. 3 friends, go down to 0. Okay. Person 1, I don't know, loosely increasing trend, I would say. Although, we're just eyeballing this, so maybe we should do this somewhat more carefully, statistically. I'm going to put this into Excel. So I can do that by typing Excel degree, because that's the name of that matrix, Excel deg. Oh, and I see it flashing at me down here, so it must be there. Make it big. I always like to add the word ID so I know what's going on here.
So the Excel command from the command line opens it in actual Excel and not the UCINET version of Excel?
Yep. The only thing about it is that it doesn't load any packages that you have in Excel. So like over in data, I have the data analysis tool pack, and it won't load that. That's the only difference. But this is real Excel. Now, if I were to draw a picture of, say, the profile of person 1 over time, I could just highlight that, go to Insert, choose a chart here, a line chart, and I get that, and then I could maybe right-click on that and add a trend line and choose an option that displays the equation. and then move the equation so I can actually see it. Now, how do you interpret that equation? The intercept is 3. That's kind of like the overall popularity of the person. The slope is positive. That means that they're kind of increasing in friends over time. There's a lot of up and down variation, but they're kind of increasing. Suppose we picked 11 here. I'm going to move this picture out of the way. Let's pick 11. And I'm going to insert a line chart. Well, that's a declining. That's actually, I mean, he had 8 friends the first week and then blew it. But I'm going to right click on that one, add a trend line, show my equation, move it up where I can see it. You see how the intercept is 3, similar to the other guy. So overall, they're kind of similar, but it's a negative slope. So this person's going down in popularity. I could do this for, let me do it for person 17. Insert. Do the trend line. Move it. You see how it's got that big intercept because that person is just generally popular, and there's a slightly positive trend too. Not much, but slightly there. Now, suppose I do that for each one of these, and I obtain the slope and intercept for every single person. What I'm doing is I'm really kind of running a multi-level model here. I'm just doing it by hand. And I've already done this, so I'm just going to open it. You don't have this. Let us hope this is the right one. Yes. So I took that in degree thing. I made a few charts like the ones we're looking at. And I also did all of those regressions, and I collected together the intercept and the slope for each person. Some of them have negative slope, some of them have positive, some have high intercept, some low. Suppose we're going to build a theory here, and we're going to predict those slopes and predict those intercepts. Come up with a theory. What predicts the intercept?
Whether you're a legacy
Well, unfortunately, this is not a real fraternity.
Oh, okay.
It's called a fraternity because it was a fraternity house, but he actually got 15 people who didn't know each other and let them live in his house for free while he studied them. Yeah. So, and this was in the 50s. It would have been great if today, because he could have webcams everywhere, and you know. Okay, so legacy.
Would the intercept be, or I guess the mean of the intercept be, of all the intercepts, be the number 3, because that's how many choices around the number 3, because that's how many could possibly go on.
Well, first of all, before answering stupidly, why not find out? But you're right, because the intercept, of course, relates to the average of the y variable. And everybody had exactly 3. But there's variation around that. So what predicts the variation in intercept?
Introversion, extroversion.
That's what I would think, yeah. I would
What'd you say, sorry?
introversion, extroversion. So suppose we used extroversion here, and we're using the correct spelling of extraversion. I think that extroversion would probably predict the overall popularity of each person. What would predict the slope, though? Now, in reality, there's probably some path-dependent things where, something happens early on and then it just keeps getting worse from there, or things get better and better. But what might contribute to this?
Sociopathy.
Well, but sociopathic, wouldn't that also affect the intercept? I mean,
I think it would, because I think that your extroversion interacting with your sociopathy might
oh,
cause a negative on the intercept.
narcissism, yes. Socioeconomic class.
I guess like how much money they have, so like.
To spend on people.
So, the more money, oh, I
If
see.
they're going out to the bar, like, and somebody has
Yeah.
the most money, they buy everybody drinks. I mean, I'm sure that's gonna boost them up.
Money. I like that. I was thinking of something like emotional intelligence. Because they didn't know each other at the beginning, they have to like figure it out. And week to week they have to like sort out, so who's doing what, and learn how to be liked. And some of them, of course, they don't have that. They got that sociopathic thing where people are beginning to discover that while they're very attractive people and they've got money, they seem nice, over time you begin to realize that we don't like them. Right? So I'm doing this very manually and saying I could predict that, but actually this is what a hierarchical linear model does. This is what a multi-level model does. And so we could do that very elegantly. Sorry?
So maybe generosity may have been a better word.
Generosity.
A lot of money.
Yeah, money is a little slimy there.
A lot of money, but they might just keep it themselves. Generosity.
Generosity. Although I do think that it'd be nice to find something that was really that predicted one but not the other. I think generosity would probably predict overall likability in general. But I think something more about like actually figuring out the social structure as you go along, learning about people and how to work them would be something that would predict the slope. Sounds terrible, I know.
Which we're assuming that group of people there's a positive desire to build friendship with them, right?
It's true. It's true. I'm assuming that. And maybe they figure, but who likes to live with people for a whole semester and not get along? I think they're trying. I think they're just not able, but you could be right.
This is also different because maybe they're friends, but 17 is just so popular that I just can't select someone else because I have to put 17.
Yeah, so there is the problem of the data structure is bad because it requires you to rank order each person. That really sucks.
Yeah, it could be just 17's the only decent person there.
Well, if he was the only decent person, then no one else would like him.
This is. Oh, by the way, I like the pattern for node 4. I didn't point that one out, but it's like he goes off his meds around 7, and then he's like manic. He's up. He's yeah.
Right, and would you consider linear slope to be an effective way in seeing, I guess, their progression upward or downward?
Yeah.
Okay. Because I didn't know, like, with variation being so great. I guess,
So high, yeah.
So great.
Well, one thing I didn't show you was the R-squares, and certainly some of the R-squares were very low and non-significant, so, yeah. Okay, so that, I have here the hypotheses and all. So this, when I put up the slides, you can go back over and see what we said about here. So lastly, we've done this actually. We did this, I think, last week with the Newcomb data, but this happens to be the Sampson data, which has liking at time 1, at time 2, and time 3, and I simply correlated the whole matrices. And what you see is that time 1, the social structure is really quite different from time 2 and 3, but from time 3 to 2, there isn't much change. And that seems to be characteristic of change in networks, that there's a lot of change at first, and then it settles down. And then sometimes there's an event that jogs the structure for a while and then slowly comes back again. Oh, so this is the one that we actually ran last week. And we showed that week 0, really different. These sort of a linear progression, and then after week 5, nothing much changes. They're all highly related to each other. Cool Excel chart of the same thing. This spine is the correlation of every week with itself, which is always 1. But you can see the very quick drop-off at first, but it's a slower drop-off later. So at first, there's a lot of change from week 1 to week 2 to week 3, and then that tapers off. Doesn't change as fast. Okay, the last thing we talk about today is, and this is anticipating next week where we talk about ego networks, but it's changes in ego networks. So an ego network is the set of people around a given person, a focal person that you're studying. So whoever, if we're decided that we're going to look at Russ is called ego. This is his ego network. And the ego network includes not just the people, but the ties among them. So at time 1 in the CampNet data set, actually week 2, Russ has as his top 3 people Holly, Bill, and Gary. And Bill has chosen Holly as among his top 3. In week 3, what we see is that Bert has dropped Holly and replaced Holly with Bert, has dropped Bill and replaced Bill with Steve, and kept Gary. Right, we see that. So we could summarize these changes. We could say, well, overall, it doesn't look like there was much change. The network size for Russ at time 1 was 3 people. The network size at time 2 is 3 people. But there were 2 people added and 2 people dropped. There was 1 person kept, and there were 12 people that he was not tied to at week 2, and he was not tied to at week 3.
You infer that this change is due to a Gary effect? So if we had multiple ego networks and we were able to see that there was a strong, there were significant characteristics of the Garys of the network.
That would be really interesting. Yeah, like I could see 2 kinds of effects. One is that when you have Gary in your network, he slowly poisons Russ's mind about the others, and Russ loses his other friends. The other possibility is that when you have Gary in his network, he tends to suck in his own friends and push out the old friends, so that everybody's network that has Gary in it starts to have Bert and Steve in it too.
So in order to test that, we would need to have some sort of value for the relationship between Russ and Gary.
What do you mean by a value?
So we would then assume that Russ's relationship with Gary at T1 was stronger than Russ's relationship with Bill or Holly, or we would just have to see it happen repeated?
I think we want to just see it happen. We'd want to see the actual changes. We don't know why it's happening. We don't know if this is a stronger tie. We might think it's just behavior on Gary's part that's doing it. Gary may smell, and maybe Bert and Steve don't have a sense of smell, so. So here's now a summary for each person from time 1 to time 2, which, as you know, is week 2 to week 3. The network size never changes because of the stupid way we collected these data. But that masks the fact that Holly actually changed 2 people. She dropped 2 people and gained 2 new ones. Carol only dropped 1 and gained 1. Jenny made no changes. Michael made no changes. Some people are loyal. Steve made no changes, for example. And, well, the loyal people, of course, kept 3 ties. And then there's the absent ties.
What is absent?
Absent ties are ones where in time 1, Holly was not connected to 12 different people. There were a whole bunch of people she was not connected to. And at time 2, she's still not connected to those people. They're kind of kept non-ties. Now, we might have a hypothesis, like that women tend to hold on to their networks more than men, who are more instrumental and just they, as soon as somebody's no longer useful to them, they trash them and bring in somebody else. So here's the number of ties kept. The mean for the women is 1.75. The mean for the men is 2.2. So that goes against that little idea. However, a little t-test shows that that difference is not significant. So men and women are keeping ties at the same rate in this particular little data set. And here I did the significance test using a permutation test, which you can do in UCINET. But frankly, I can't see any reason why you couldn't just do this in regular stats. Any questions? Yeah.
So, we have this number of observations, 8 and 10, and I know those are the people, but if we were running, let's say, dyadic regression, and we were looking at or that logistic, and looking at the probability that the tide changes, we have a lot more observations.
Exactly.
Would we expect a difference in result in that method?
Interestingly, not exactly, no. Because it's comparing it against all those random things with the same n. So, like, you can do an experiment. Suppose you correlate age and income. Now, you take age and you convert it into a matrix, which is the difference in age between every pair of people. And you take income and you make difference in age in income between every pair of people, and you run a QAP regression, you get the exact same correlation if you had just correlated the two simple variables in the first place. The next bit gets involved. So I think I'm just going to hand wave it, and then we'll pick it up next time. But one thing that's of interest, here's Russ's network at both time periods. So the reds are ties that were there only at time 1. The blues are only at time 2. And the grays are the ones that are at both. So if you remember, Russ has Bill and Holly in his network. He drops them both in favor of Steve and Bert, but he keeps Gary.
So it's reciprocal in the time T2.
It's reciprocal.
And Russ in T1 is saying Bill and Holly, they're not saying him.
Yeah, actually. And
Bert and Steve are, it looks like, directing to.
they are. You're right. You're right. And that's interesting. So maybe Russ drops Bill and Holly because it was unrequited love. It's like, I'm sending out to you and you guys are giving me nothing back. So I'm going to go for those two people that actually have shown me some love. Very good observation.
There's the love there.
Where is the love? Well, because there's a blue tie that's going into Russ. That means that... Oh, wait, those are time 2. Oh, too bad. I was so caught up by your interpretation that...
No. They're gray arrows going into Russ, right? So they select...
Oh, yeah. You're right. You can tell by the arrowheads that they're gray. You're right. The one very huge limitation with NetDraw is that it can't draw two separate lines. Like, it can't draw one line to Bert and a separate line to Russ. And so whichever one got drawn last gets the color. So anyway, but let's just get to the larger point here. When you add new people, are they just plain strangers that you add, or are they typically people that you already had in your network? And if you notice that when Bert dropped Bill and Holly, who were not connected to his friend Gary. He adds Bert and Steve, who were connected to Gary. So it's almost like Russ added Gary's friends to his network. We can measure that. We can measure how many of the new ties are friends of friends, friends of existing friends. And there's a lot of variations in this, which is why I don't want to get into it. But we can do that next time. But we're trying to get at now like the motivations. We see the network changing, but why is it changing it the way it is? Well, maybe one reason is that Russ is being introduced to people by people in his existing network. Or it could be a characteristic of Russ that he can't really adapt very easily. It's not easy for him to pick up strangers as friends. The only way for him to get new friends is if they're kind of already pre-vetted by his existing friends, his existing network. All right, next time, ego networks, structural holes, the big concepts in the field. I will post this and the ones that apparently I didn't post, even though I swore I saw myself post them.
There's a post, but there's no link. You cannot click the link.
Oh, so that means, by the way, when that happens, if you just go scroll down, it will be down at the bottom of the page. Yeah.
When you said that you recorded it, so are you posting them on the recording on the page too, or is that on Canvas?
It's not on that. It's going to be on the page, and I haven't posted it yet.
Okay.
I wasn't sure, it was like a 3-hour movie. I don't know even how to post that. So I better tell it to stop recording now.
Steve,
Yeah.
it's like